thank you for inviting me to this. What I want to explain today is a relation between two subjects. So one of them is multiple zeta values, and the relations, algebraic problem of algebraic relations between these numbers, and the relation of this problem is the chain theory of homotopy invariant iterated integrals. So it's going to be, in fact, it's an old relation which is known, it dates back to the works of Foucault in 2009, and recently it has been revived, so it's, there is some new result in this direction, which will do in particular to Alexeyev and their collaborators, and so I want to report on it. So the plan is this. So there is multiple zeta values. And we will see that there have two kinds of family of relations. There is a double shuffle relation, and there are associator relations. So, in fact, there is a result, a theorem by Foucault, that associator relations implies double shuffle relations. And in fact, the proof of that is based on chain theory, so homotopy invariant, iterated integrals. And this is really the proof is based on that. In order to explain the story, maybe I will start with the end and with the chain theory, because it's a general theory which is very interesting to know, and it also relates with the subject of this conference, namely shuffle algebras. And then I will explain the beginning and how this theory helps prove this result. Okay. So that's the plan. Okay, so let's start with the chain theory. So let's M be a smooth manifold. And we take E, it's differential graded algebra of the differential form. And if I take, so E1 of M, it's one form. And I may take the shuffle algebra over this E1 of M, so that's what people denote as TC of EM, so which I will denote also E shuffle of E1 of M. So it's just the tensor algebra sum of E1 of M to the power N, but with shuffle product. So it's a commutative algebra. Okay. So we say that A1, AN plus 1, AN plus 1 is sum of A sigma 1, A sigma n plus 1. Okay, and if I have such an element here and a path, I can integrate such an element on this path. So I can do a map from a shuffle of E1 of M cross path of M to C, and here gamma and then A1 AN. I can actually to see the iterated integral on gamma of A1 composed with AN. So it's called iterated integral. The question is, yeah, it's well defined, but the thing is, when does it depend, was it a homotopy invariant? So the point is that in general, there is a if you do a small deformation of gamma, when is it going to be invariant? So the answer is, so there is a differential to consider. So the thing is, you are doing the following map, delta. And the map takes A1, AN, the sum of you are doing here. So A1 AI minus 1, then times AI product with AI plus 1, and then times AI plus 2, and then plus the sum, and there is no signs, sum of A1 AI minus 1, then DAI, and then AI plus 1 AN. So if you belong to a curve delta, so the fact is that then in fact a kernel of delta, so in fact the kernel has not to be necessarily homogeneous, it can be a sum with different degrees. So if you do the iterated integral of the element of curve delta, so the point is that you have if you restrict to this curve delta, then it descends to pass modulo homotopy. Okay. That's one thing. So, in fact, the point is, curve delta is also, so this is a Hopf algebra. Is inside a Sch of E1 of M is a Hopf subalgebra. Yeah. And okay, in fact, the point is that then you can use, for example, if x0 is a particular point of M, and we fix a lift a universal cover M tilde over M, and x0 tilde above x0. Then we get a map going from curve delta to functions on M tilde, okay, which to gamma associates to an element A associates the integral from x0 to the map taking x tilde to this integral to x0 to x tilde on M gamma of this A. And this is an algebra morphism. So this is, in fact, the starting point of chain theory. So the point is as follows. So in fact, chain theory. So in fact, the point is that you then do the following, then you can continue the map. For example, then you map from curve delta to say infinity of M tilde, and then you map it to functions on the pi1 of M. Okay. In fact, you map this to f sub A, which is the image here. And then you can map this to the map taking an element of the pi1, say gamma, or alpha, let's say an element, to f alpha, of A acting on x0 tilde. Okay. So this is functions on pi 1 of m. Okay. And in this way, then that's one thing, but it's not what one usually does. In fact, so in the application that we will consider, in fact, we will also look at some algebra, some DGA, some model of E star of M. So what is a model? A model is a DGA which has a DGA morphism to E star of M. Okay, so it's going to be C plus V plus W. So it's a small DGA. It's a DGA which has a DGA morphism to E of M. Okay, and then in that case you have a morphism from let's say set delta underline. It's going to be the map going from chevy to chevy times W times chevy. Okay, so defined analogously. So then we have a commutative diagram relating delta underline with che of E1 okay, and then in particular a map from ker of delta underline to ker delta. So we have a cycle of maps, and from there to functions on pi 1 of M. Okay. And here you get in connection with the holonomy what is called holonomy algebra. So in fact, the thing is that in that case, so in particular, so we assume that V is a subset in ker of differentials from E1 to E2. Okay. Then you know precisely what is ker delta here. It's the restricted dual of some enveloping the algebra. What is this enveloping the algebra? So you take 3D algebra over V dual over quadratic relation. And what is this relation? It's you are taking the kernel of H2 VW, and then you take the orthogonal of this, which is a subset in Li2 of V. So this is 3D algebra over a vector space. And then you take this ideal lattice. So it's a quadratic the algebra. Okay. And so what we have from there is that we get a map going from pi 1 of M by evaluation to so in fact the spectrum of this ker delta, but this spectrum is the exponential of this algebra. So it's an exponential of this Li of V dual completed over this idea. Okay, so this is in fact you get in this way a representation in fact of a group morphism from the pi 1, so from total group of the manifold to some here in fact exponential of nilpotently algebra. So free it's a positively graded algebra. So it's a nilpotent group, and so in fact it's a morphism from pi 1 of M to some nilpotent group, and therefore it then you get a factorization through the Malchev completion of pi 1 of M. So in fact you get for free you have pi 1 of M of C which is the Malchev completion, and then you get in fact such a map. This is coordinate map. Okay, so let's look at some examples. So in fact, there are many ways where this construction helps you compute the Malchev completion of pi 1 of a manifold. Okay. Fact. This is this may be an ISO. Compute pi 1 of m. And so we'll see some examples.
This looks like a very general construction. I mean, because you started off with something like one forms that kind of want to pair with pi 1, and you get this kind of map from the Malchev completion. Like, do people do this for like?
Well, here, in fact, you're right. So, in fact, here it's very general. So, in fact, you usually want this to be a quasi-ISO. Okay, in order to make sense. Otherwise, the V is 0. Yeah. So in fact, yeah, you really want V to be the same, it's a representative of this H1. Yeah, in order to be for this to work. Okay. So we'll see some examples. Is it your question? No.
I'm just wondering if like do people do this with like instead of pi 1 of m, it's like, you know, some absolute log group or something like.
Yeah, no, but this is a DG, differential geometric construction. So there are examples, there are, you can generalize, no, but here we are in this section. Okay. So let's see some examples. So first example is when you have m is p1 minus 3 points. This is also m04. Okay. In that case, you want to say that V is the span of d log z, d log z minus 1. So which we call omega 0 and omega 1. Okay. And then, in fact, you have just a quasi-ISO. So, in fact, C plus V to E star of P1 of M is a quasi-ISO. Okay. And then, in that case, in fact, you have no W. Okay. And then it's just that pi 1 of M here is a free group F2. So, and then you get in this way a map, so you get a map to X of the 3D algebra of omega 0 star, omega 1 star, which we call E0, E1. And in fact, when you go to Malchev completions, it's an ISO. Okay. And the map here is obtained. So in order to the map here, so the generators x0, x1, so they are mapped to complicated things. So in fact, if you want to write this explicitly, then you will say that, for example, so let's say that your base point is close to the point 0, okay, or rather close to the point 1. So then you will say that x0, x1 will be this generator, and x0 will be that generator. And then you will say that x1 will go to exp of 2 pi I E1, and x0 will go to some conjugation of exp 2 pi I E0, and conjugation by some series which is called KZ associator. So in fact, phi KZ. So a series. The KZ associator, the Knigin-Zamolchikov associator. Okay. Well, a second example. M is M05. So M05, so you may view it as a point in, so it's a point, so it's a path of xy in A1 square, such that xy, so it's like this. So in fact, so x different from 0, 1, y different from 0, 1, and xy different from 1. Okay. And so in that case, the situation is more complicated because then you can say that V is just spanned by so d log x, d log y, d log 1 minus x, d log 1 minus y, and also d log of xy minus 1. So it's a 5-dimensional. And then, in fact, there is a non-trivial map to, so wedge do of V goes non-trivially to E2, in fact. And in fact, so you can construct a model, but it's not a free algebra, okay? And the algebra that you get in this way is the so-called algebra P5. So, in fact, I just LV star, so holonomially algebra. So this so-called is the holonomial algebra, so holonomial algebra. So this is so-called P5, and P5, so it's a algebra generated by Eij from Ij from 0 to 5, Ej equals Eij, I and j are distinct, and then you have relations. So you say that Eij Ekl equals 0 for Ijkl distinct, and sum of Eij for all j, and for any I, this is equal to 0. Okay. So in fact, this is the associated grading of the group, and which group? It's in fact the pi 1, so the braid group of 5 points on the sphere. So, pi 1 of integration space of 5 points on S2. Okay, so times C, for example. So in fact, so this can be computed, and then in that case, what we get in this way, we get a map. So we get a map from pi 1 of M05, which is not far from this group. It's about the same as this, up to a Z2 group. And from there to this X of P5. And so in fact, if you go to Malchev completion, it's an ISO. Okay. Good. So okay, this is a bit of theory. So it's interesting by its own, and so it's this chain theory. It's so it's very much related with Malchev completions, and so it's useful for this. But here we are going to apply it to something different, namely to this problem of relations between multiple zeta values. So if there is any question on this part, it is the time for it, because now we are going to move to another topic. So the MZV, so these are the numbers which are obtained as the iterated integrals that we saw in the first place. So in fact, you can do, let me give a definition. So in fact, zeta of K1, Ks is by definition sum of so it is iterated sum, and it makes sense for K1, Ks greater than 1 and Ks greater than 2. Okay. So these are just complex numbers, so these are even real numbers. Okay. But in fact, the interest of these numbers is that they are also periods, so iterated integrals, and in fact, this is so-called the contribution formula. So this is iterated integrals from 0 to 1. So you have to put omega 1, then omega 0 to the kx minus 1, etc. Omega 1, omega 0 to the k1 minus 1. Sorry. No.
Those are the same forms in the example, the example 2.
Sorry?
Here, omega 0 and omega 1.
Yeah, it's an alternation of M0, but I want to find the omega 0. Yeah, I think so. You start omega 1 being close to 0, and in this way. Okay. And okay, so good. And so the question is to find algebraic relations between them. So there is one type of algebraic relation which is implied by the in fact that the fact that these morphisms are algebra morphisms. So the fact. So if you do the integral. So the fact that this is expressed as a shuffle and the shuffle sum. So for sigma in skl of omega alpha sigma 1. So this implies a bunch of the shuffle relations. Between the MZVs. So this just says that you have an algebra morphism going to C from some subthing of the shuffle algebra. So you have the shuffle algebra in omega 0 star, so in omega 0 star plus omega 1 star. And you have a subthing here, because in fact you don't want all words, because not all words will be convergent, because the point is that you are integrating from 0 to 1 and you have singularity. So in fact, you want to avoid singularity. Here you have subalgebra, so in fact you have to take C plus in fact, omega 1 times concatenate with the shuffle algebra, and then concatenate with omega 0. Okay? And the point is that this is an algebra morphism. It just is expressed by the fact that you have this this relation. So it's a set of relations. And another set of relations is the so-called Stoffel relations. So in fact, such is relations between. So there is this fact that this MZV satisfies the so-called shuffle relations. And now we are going to be interested in other relations, which are so-called Stoffel relations. What is Stoffel relations? So they depend on this writing of zetas as iterated sums and not integrals. So Stoffel relations say that, for example, zeta of A times zeta of B is sum of 1 over A and times sum of 1 over M over B, to the power B. And so it's going to be a sum. You can decompose N and M in 3 ranges. So N smaller than M, N larger than M, plus N equals M. And so this is going to be zeta of AB plus zeta of BA plus zeta of A plus B. Okay. So it's a relation which is called a Stoffel because it's like you are shuffling cards, but sometimes these cards can stick together. So it's a mixture of sticking and shuffle. Okay. So if the cards do stick together, for example, like this. So and for example, I have values here, alpha, beta, gamma, and here delta, epsilon. And for example, if these two cards stick together, then I have just one card, and the value is beta plus gamma. Okay. So in fact, this is an example of the Stoffel relations, and you can well understand that you have a big series of Stoffel relations, and so you have. So I don't write the details. So, but then you have the Stoffel relations. Okay. And plus you have extra relations called the regularization relations. So I don't go into it. And there is a theorem by Racine. So Racine, 2002. It tells that, in fact, if you take the Q, so if you take the ring of interest, you are going to take the formal analogues of the zeta number, so zeta formal of n1 and k. Okay, and also so and then which you where you kill. In fact, you need some formal analog of 2 pi I. And you have some relations relating zetas, like Bernoulli relations and so I don't discuss them. But then over the if you take shuffle plus Stoffel relations and plus regularizations relations. So this is a spec of this. It's a torsion over some algebraic pro-algebraic group, which is in fact a pro-algebraic group. So in fact, so if you localize in 1 over 2 pi I, this the pro-algebraic group, so you call it DMR. And it goes in an exact sequence where with which is a semi-direct product of some DMR0, semi-direct product with a multiplicative group. And this one, it's a pro-unipotent algebraic group, and so it's defined by its Lie algebra, so Lie of it's a graded, a positively graded complete Lie algebra, which is known relatively explicitly. So in fact, which can be defined by explicit conditions. So yes, and in fact we will need the explicit form of this algebra. And so let me give more indications on this. So in fact, the point is you have the 3D algebra in E0, E1. And this thing, it's a 3D algebra, but you equip it with, so it maps to derivations of itself by A maps to D sub A. Which is a derivation, so E1 maps to 0, E0 maps to bracket A E0. Okay. And so there is a unique Lie bracket on Lie of E0, E1, such that this is a Lie algebra morphism. So that's also called IRMA bracket. And in fact, DMR0, so the Lie, so it's called DMR0. So it's in fact it's a subthing of Lie E0, so it's a set of all psi in Lie of E0 E1. Such you have a delta star of psi star. So psi star is the primitive of the delta star. So in fact, it's psi star times 1 plus 1 times psi star. So what is delta star? What is psi star? So in fact, you have to say that psi star, it's psi plus 1 over n coefficients of E0 to the e minus 1 E1 times E1 to the n. And then you have it act, so the projection of it. Projection, so where pi is a projection. So you map from Q of E0, E1. So then you kill the left ideal generated by E0. And then we identify it with a Q plus Q of E0 E1 times E1. And so this is pi. And in fact, delta star, it's a map mapping that to its square. And taking, so if you take here, the element y sub n is to be E0 n minus 1 E1. is going to map y sub n to yn times 1 plus 1 times yn and plus the sum of yk times yn minus k. And this is delta star. So in fact, since this algebra here is freely generated with elements to y sub n, this delta star is well defined, and therefore it's well defined to impose that this psi star will be primitive. So it's a rather surprising definition, because it's by no means clear using this definition that this is going to be a list of algebra of that IRMA algebra for the Lie bracket, but it's indeed. Okay, so this is one big set of relations. Another set of relations is so-called associator relations. So here, in fact, these relations are much more familiar. So in fact, the thing is, we have this element phi. So in fact, so we go. It's based on the geometry of moduli spaces. So it's based on 0, 4 and 0, 5. So in fact, the point is. In fact, you are interested in the holonomy of the so-called KZ differential equation. So in fact, so you just say, so if you are interested in the PX, let's say renormalized holonomy, of the connection d minus E0 d log z plus E1 d log 1 minus z. Okay, from 0 to 1. So this is some element which is called the phi kz. Okay, so kz associator, and this belongs to C double bracket E0 E1. Okay. So because it's a holonomy, so in fact you do the path order exponential of, so here you have this connection, which is singular at 0 and singular at 1. And so what you are doing is the path order exponential from 0 to 1 of this connection. So of course, as such, it is not defined because you have singularity, so you renormalize here near 0 and near 1, and this renormalized holonomy is just your element. And the thing is that you have this expressed in fact, as you can imagine. So here you have omega 0, and here you have omega 1. So this expresses as a combination of iterated integrals of the E0s and E1, and as such, so it's a generating series for the MDVs. So in fact, the formula is here. So you have so KZ. So it's 1 plus sum of minus 1 to the m of the zetas of k1 km. And so, in fact, you have an element W of K1 Km, which is a word. And this word expresses at, so E0 K1 minus 1 E1, etc. E0 K1 Km minus 1 E1, plus explicit terms, words with starting with E1, and ending in E0. So in fact, you can view, in fact, this phi kz as a generating series in the zetas, in the multiple zeta values. So this was first found in a paper by Lee Murakami. And the point is that this phi kz, this element, satisfies the so-called pentagon relation. So phi kz the pentagon relation which is written like this. So phi 1, 2, 3, phi 1, 2, 3, 3, 4, 5. Equals 1, where these are morphisms. So in U, P, phi, where x maps to x, I plus 1, I plus 2, are some explicitly defined morphisms or are morphisms from Lie of E0, E1 to P5. So I could give the explicit form, so it's not difficult. So in fact, the point is that you have these relations, and this in fact is a consequence of well, the existence of differential systems, so-called KZ differential systems. So in fact, this is due to Drinfeld, and it's based on the existence of KZ family of differential systems. On the M0 ends. Okay. And as such, this implies a bunch of relations on the MZVs, because you remember that the phi KZ is a generating series for the MZVs, and so this implies the associator relations on MZVs. Okay. And so you can, similarly to the Racine case, you can construct a torsor, or a scheme, first of all, of these relations. And this is the so-called scheme of associators of Drinfeld. And in fact, the structure of it is also known. So it's now Drinfeld's theorem in the 90s. So in fact, if you do the spectrum of zeta f of n1 ns then 2 pi I formal 2 pi I formal inverse over associator relations. So it's the same result. So it's a Lie torsor. It's a torsor of algebra. So same story. But now the group is called GRT. Is a torsor over GRT, which is GRT1 semi-direct product with GM, and Lie of GRT1. So GRT1 is a pro-unit, and Lie of GRT1, it's again graded, positively graded Lie algebra. And so GRT1 also can be defined explicitly. So in fact, it's also a subalgebra of the IRMA Lie algebra. And so in fact, GRT1, so it's a kernel of, so you have the map from Lie of E0, E1 to P5. And so it's going to be the map taking psi of E0, E1 to a sum of psi of I plus 1, I plus 1, I plus 2. And in fact, again here, there is a small surprise, is the fact that it's the kernel of just a linear map, and this is nevertheless a list of algebra of the IRL algebra. So it's surprising because this is not the algebra morphism for the IRA bracket. So in fact, you can't put here on the P5 such a Lie bracket that this would be a Lie algebra. So it's okay. So. Okay, and so now the result, Fugusho's result. Is that in fact one torsor it contains the other torsor. So in fact a spec over associator, it's a subthing of spec of the same algebra over double shuffle. Relations. So in fact, associator relations imply double shuffle relations. So this is this was first proved by Fugusho in 2009. Okay. In fact, earlier there was an attempt by Deligne and Terrasoma in 2005, but they didn't finish their preprint. So Deligne and Terrasoma. But then, in fact, with Fugusho, we read carefully the paper of Deligne and Terrasoma, and we finally understood what they wanted to say, and finally we wrote also a proof based on their ideas. Then, so it was in 16, I think. Yeah, and recently there was a contribution by, I think, Alexeev. Severa, so let me invent Naef. Hogwarts. Naef. Rennes. And Naef, Rennes, etc. 2006. 2026. So it's not a new proof, but it's a contribution to a better understanding of the Fugusho's proof, in fact. So in fact, let me now try to describe the proof of Fugusho and explain it with a new understanding coming from this recent work. So the point is, in fact, in order to prove this, it's two torsors. But these two torsors contain a particular element, which is phi kz, so this associator. So in order to prove that this torsor is included one in the other, in fact, you just have to prove the inclusion of the algebras. So just proof, so needs to prove only that GRC contains in GMR.
Sorry, double shuffle, you mean the shuffle and staffel relation?
Double shuffle, yeah, it's a shuffle plus staffel. Okay. And here is the picture, in fact. Then there is a commutative diagram. So in fact, we then, in fact, we first define this subalgebra of P5. So P50 is the kernel of, so we do Pre1, so Pre1. Where Pre-I is going to P5 to so the free Lie algebra in two generators. So which takes EI j to 0, and then AKL, so to some A, and A EKL and EKL prime So in fact, there are such morphisms. So morphisms are just corresponding to erasing of points. Okay, and so you take the intersection of three such morphisms. And the point is that then you have the pentagon. Then there is commutative diagram. Like this. So in fact, Lie of E0, so free Lie of E0, E1. You have the pentagon. So pentagon co-restricts to this P50. In here you have the abelianization. And the point is that, in fact, here you have the map delta star tilde, which is so it's the map taking x to delta star x minus x1 minus 1x. And so it's going to go in this algebra. So you have this y sub I, which we defined somewhere. It is here. Okay, so this is q bracket, double bracket of y sub i's. Okay, and so we map this to q bracket of y sub I squared. And the point is that here we have an isomorphism. Okay. So in order to prove that, so it means that in fact the thing is that this kernel, this kernel here, which is DMR, is just the kernel of, so it's a pentagon composed with abelianization. And therefore, so if you are in the kernel of the pentagon, then definitely you are the kernel of delta star. And the reason why, so this diagram is not evident. And in fact, the point is that here, in order so the thing is that it's composed in two commutative triangles. This triangle, in fact, this is where AH and RS come in. So in fact, they prove it. And the map here is so it's a direct sum of so LAB. So AB are multi-indices. So in fact. The point is that you prepare maps from UP5 to C, so linear maps on UP5, and such maps, so you call them L, A underline, B underline, so which, so AB are A, it's A1, AP, B is B1, BQ, and so these are integers. And this is obtained using, in fact, you remember that you have an element here. So it's an element of the bar complex, in fact. So you have this kerr delta. So you remember that you have this kerr delta coming from shuffle of V to shuffle of V times W times shuffle of V. So you prepare sufficiently of these maps. So you get some such elements of such elements. So these elements here belong to this bar complex, so it's called bar complex, and but this Hopf algebra, and it's just the dual of UP5. So you explicitly construct dual elements to just elements of the dual of UP5, and this is the elements that you are going to construct your map. The map here is just the map like taking X to sum of LAB of X times Y A1, Y AP times YB1, YBP. Okay, so this is a map. So in fact, so this is it. So the precise reason why, so in fact if you want to analyze, so the Foucault's proof, initial proof, was using These elements precisely, and so I was constructing an argument using a pentagon relation, so it was a bit complicated, but in fact the transparent way to think about it is, I think, we now think using this result of Alexeyev and company to say that we have this commutative diagram. And so this is it. So this is some progress in this direction, and hopefully it makes this proof of Foucault easier to relate with the alternative proof of the Linterasoma that we finally wrote down. So this is it.